Hello, welcome. My name is Mastro Castro Nuovo for the Italian Space Agency, and today I'm going to tell you about the Hyperspectral Prisma Italian system and how it works, and of the applications that can be developed with its data. So, what is the meaning of hyperspectral remote sensing? It is the basis of the functioning of the Prisma satellite. The sun radiation illuminates the Earth, and part of that radiation is reflected into the space. The Italian satellite Prisma carries on board a hyperspectral remote sensor that collects this radiation reflected in order to create images that then it's divided into the spectrum into many bands, even beyond what's visible. The objects on the Earth's surface leave some particular unique prints along the spectromagnetic trace. Cataloging them, these prints, known as spectral signatures, they allow the identification of the materials that comprise an object and their analysis. Here you can see as an example the spectral signatures of the naked soil, of the water, and of the vegetation. What's the difference between a hyperspectral system and a multispectral system? It's just the number of bands or spectral channels. For instance, the multispectral satellites, Landsat and Sentinel, they carry each 9 and 13 bands. Prisma carries 240. So we can observe the radiation reflected from the Earth's surface with a better detail that allows distinguishing between the different materials. We observe now which are the objectives of the Prisma mission. As I have already stated, Prisma detects sunlight reflected from Earth in 240 bands or channels between 400 and 2500 nanometers. In other words, from what's visible to the infrared of short wave. The combination of the bands and the radiometric data enables to recognize the chemical, physical characteristics of the elements present in the area observed. The applications are many. For instance, the detection of changes and the coverage of the soil of the Earth, the hydrology, erosion of soils, the search of gas and oil, and many others. The technique of obtaining hyperspectral images enjoys an extensive experience on sensors, airborne sensors. However, the spatial and temporal coverage is inherently limited. The technology of hyperspectral instruments is very mature and flight proven. Since 2008, some hyperspectral missions have started their development, both in Europe and worldwide, among them Prisma. What are its milestones? Prisma was launched on March 22, 2019. It represented a huge historic event for Italy. It is a program totally national, funded and developed by ASI, and with a number of Italian industries. It was also launched by a Vega rocket designed in Italy by the company Avia. We observe now which are the most important data of the mission. The satellite is in an Earth orbit, the LEO synchronic, at 620 kilometers of altitude. The lifetime of the operations is expected is for 5 years. The coverage is global, worldwide. It will cover the whole planet except the polar caps. The primary mission of the mode is user-driven. The system is capable of observing with a swath of 30 kilometers and a GSD on the soil of 30 meters, and hyperspectral, and 5 meter in the panchromatic. Every day are observed more than 200,000 square kilometers on 15 orbits, and they can be processed 200 hyperspectral scenes of 30 by 30 up to the second level of the product. The satellite passes exactly over the same trace every 29 days. It's a revisit time, while it can observe the same area every 7 days. That's the relook time. We observe the key points of the system architecture at a glance. The dry mass is of 827 kilos, from which 202 of payload. It has a dimension of a small car. The center of control center for the mission and satellites are in the city of Fucino, 100 kilometers from Rome. The center for the elaboration of the data is in the city of Matera, in the south of Italy. The launching, as I have already expressed, was made by Vega. The Prisma instrument is composed by a high spectral resolution spectrometer optically integrated with a medium resolution panchromatic camera designed to acquire all available bands in the spectral range between 400 and 2500 nanometers. The surface may be observed in the latitudes of 70 south and 70 north to any longitude. Prisma uses the concept of sensor of vertical broom or push broom, so the observer is observing every time. It takes 4.31 milliseconds to acquire an Earth surface of the satellite itself that measures 30 kilometers by 30 kilometers and completes the image of 30 by 30 with the movement of the satellite in 4.31 seconds. It may acquire without any interruption up to 1800 kilometers. Here you may observe the main characteristics of the payload. For example, the size of the pixel on the soil is of 30 meters in the hyperspectral channels and of 5 meters in the panchromatic channel. The quantification radiometric is of 12 bits. The radiometric quantization is 12 bits. There you have 175 kilos of optical head, 25 kilos of thermal shield, and 11 kilos of main electronics. That's the mass. For the power consumption required is of 90 watts for the observation and 80 watts idling or at rest. The optical head collects the radiation through a telescope, disperses the radiation by the two spectrometers, separates the pan channel using, and it turns the photons into electrons by means of state-of-the-art detectors, and the main box has the function of controlling the instrument and to handle the flow of bits representing the spectral images up to the interface with the SC electronics. Now we observe the light path within the instrument. The telescope is common to the hyperspectral channels, and panchromatic. This in field separation between the hyper and panchromatic is observed in the optical field. There is a singular tray or a single pass, or this separation, this splitter for the vernier and sphere channels is obtained with an ACE divider. The vernier and sphere are obtained through a prism. There is a unit, an internal calibration unit that can use the sunlight or the parabolic mirror. Spectral images. So the optical head observed here, the thermosiphon, the triphasic, the plate of the payload for the interface with the satellite. Here you can also observe the dimensions as well and the weight. This is another view of the optical head. Yes, you can see the covers from up front, the cold radiators, the covers, the optical bench, the heat pipe, the main port entrance. the optical pathway of the light in the upper part of the instrument. We can observe it here on the optical bench, on the upper part of the optical bench, and the mirror, foldable mirror, directs, yes, to the lower plane. In the lower plane, the light beam follows different pathways depending on the bands of the spectrum: the panchromatic, the visible, the infrared, the near infrared. Now we observe which are the objectives. Prisma supports several United Nations goals into the 2030 Agenda for Sustainable Development: zero hunger, clean water, communities, sustainable communities, clean water, production and responsible use, action for the climate, submarine life, life of Earth ecosystems. Some examples of products with added value related to sites everywhere, cities everywhere. Here you can observe examples in Canada, in the United States, in Peru, in Italy, in Iraq, in the mid of the Pacific. Now we observe this example in the United States. This site in Nevada has been used as a site of test for the detection of minerals, extracting the spectral profiles of the pixels within a data cube and comparing them to the library of spectra of the known materials, for example, the kaolinite. What we do is to compare the spectral signature from the kaolinite that you have in the library, as you can see here in black, with versus the Prisma spectral profile in red. And here we can observe that they match, they're close. On the map on the right, we observe in red the rich areas of kaolinite. Another example is the site in Margherita di Savoia in Italy. Here you can observe these images. To the right, the image has already been treated. Here there is a salty area, and we can observe the properties of the water and the characteristics of the salt. In this map, the deposits, where the water is saturated with salt, they are showing in red. In this other site in Italy, Sabaudia, not far from Rome, it is detected the depth of the ocean close to the shore. Here you may observe it with different colors. In this lagoon close to, in central Italy, we get to obtain the turbidity of the water. This property is related to the water quality itself. There is also an example in Peru, in Cerro Verde, in Arequipa. In this area, we can identify where there is a vegetation with a higher content of water. Here you may observe that the vegetation that contains more water tends to the green. It's greener, while with less water will have a red color. In this area of the coast near Rome, in Castelfusano, there is a map of the state of the vegetation of forests. Thanks to the hyperspectral images from Prisma, we may detect both the content of chlorophyll as well as the content of water. And this obviously is related to the status, the condition of the forests themselves, of the vegetation itself. In Iraq, in this city of Basra, it is detected some hot spots and smoke plumes originated by the gas flaring. Here we can observe a detail. And what we can obtain is a map of the presence of hydrocarbons. Here, for instance, in this site, we detect a spectral as it is shown in this chart, this slide, and you can observe that it corresponds to the profile of hydrocarbons. In Canada, we compare two images in the Veneer band and sphere bands in this area of Vancouver. We combine the information contained in the images for the different bands, and that's how we can perform coverage maps of the soil, for instance, to detect where there is a jungle, snow, clouds, naked soils, harvests, wet lands, urban areas. This is detail of the airport area, where we can observe the different layers or covers here on the right, different covers. And here we have the last example. In the center of the Pacific Ocean, there is an area known as the Great Pacific Garbage Patch. Means big garbage patch in the Pacific. Here in this sphere image, we can observe some clouds in black and a shadow in red, and in white possibly those are the spots of floating plastic debris. So we passed the satellite exactly on that area that believed to be the most likely for the presence of this debris patch, garbage patch, and we have detected exactly these white spots. Comparing the spectral signatures detected in these white spots with the spectral signature of the plastic, we obtain a good agreement or good matching. So this was all. Thank you so much for your attention. I hope you have liked it, and for any other information you may write to us to the email in the last slide, email address in the last slide. Thank you so much.